much for coming to my talk on extending Intel-x86 consistency and persistency. I'm Azalea Raad, and this is joint work with Maranget and Viktor Vafeiadis. I should also say that Alan and James are a particularly tough act to follow, so please bear with me. My talk is nowhere near as interesting. There's no sketch, but if it makes it more palatable for you, you can think of it as a conversation between me and me. So let's get started. As the title suggests, our work is all about understanding the formal semantics of Intel-x86 memory types and non-temporal stores. So let's start with a quick overview of what these features actually are. As you may already know, the Intel-x86 architectures provide two types of store operations, plain stores and non-temporal stores. Plain stores are probably the ones that you're familiar with, where the result of the store is cached in order to enable faster and more efficient later accesses. By contrast, non-temporal stores, as the name suggests, completely bypass the cache hierarchy, and they go directly to memory. They're non-temporal, as in you shouldn't rely on them later on. The result may not be valid. As a result, they're not cached. And this is particularly useful for avoiding cache collision, and it turns out these operations are ubiquitous. They're used everywhere within application-level code. For instance, a quick search on GitHub for the move MPI instruction, which is an Intel-x86 non-temporal store, returned over 300,000 results. It's also used all over the place within the C runtime as part of memcopy, for instance, and as well as other large-scale projects such as PMDK, SVDK, DML, and so on. Additionally, Intel-x86 also allows you to declare the memory cacheability of a given page. So memory cacheability can either be non-cacheable or cacheable. So when you declare a memory page as non-cacheable, it means that accesses to the locations in that page will bypass the cache hierarchy. They won't be cached, and they will actually directly interact with the memory. There are two non-cacheable types, the strong uncacheable type, or UC, and the right combining type, or WC. By contrast, the cacheable types, as the name suggests, do go through the cache hierarchy, and there are two of these, the write back type, or WB, and the write through type, or WT. Also to mention that if you don't explicitly define the memory type of a given page, by default, it will be allocated within WB memory, so or write back. And once again, these features are widely used within system-level code, for instance, within the Linux kernel. Now, as semanticists, our main interest in these features was understanding their behavior and understanding their formal semantics. So at this point, to this end, we have developed this model we call Ex86 for extended x86, that is the formal consistency semantics that includes these additional features, namely non-temporal stores and memory types. Now, at this point, you might be wondering, well, I've always known Intel-x86 to follow the simple total store ordering, or the TSO model. Isn't that just the same? In fact, the established literature, that is the seminal work of Peter Sewell, Scott Owens, and others, have told us that Intel-x86 architectures are subject to TSO. But it turns out that in these papers, in these works, we only considered the default memory type, that is to say, the WB memory. And it wasn't clear to us whether the rest of these features, the rest of these memory types also follow the TSO model or not. And just to give just a quick reminder for those who are not familiar with the TSO model, TSO is a weak memory model, but is the strongest weak memory model. Some of us call it the gateway weak memory model, as it were. And conceptually, you can think of it in an operational way as follows, where you have multiple CPU cores here, and of course, the interactive memory at the bottom. But in between the memory and each core also resides a core local, a core private store buffer. So every time a core issues a store operation, a plain store operation, you can think of it at that store being delayed in the store buffer, and at some point in the future being propagated to memory and becoming visible to other threads. Every time the core issues a read, it will first go to the buffer to see if there is a pending write store there, otherwise it will go to memory. And this is how in TSO we capture the write-read reordering by delaying the stores in the buffer. Because if you have an earlier write store and a later read, then if you because the store can be delayed here, the read can overtake it, and we support store read or write-read reordering. And once again, remember, we are interested in seeing the consistency models and the possible reorderings of these different memory types, and to confirm whether or not they also follow TSO. So to answer that, let's look at two canonical litmus tests that we in the weak memory literature are very comfortable with, namely the store buffering litmus test and the message passing one. As you already probably know, in the store buffering example, we have two threads, two memory locations. Let's for now assume they're in WB memory. No, actually, yes. For now, let's assume they're in WB memory. And of course, initially they both hold value 0. Now the left thread issues a store to X with value 1 and then reads from Y. The right thread stores to Y and reads from X. And our question we want to ask is the annotated behavior allowed? I.e., is it possible for both of these reads to read the initial value and ignore the earlier writes to X and Y? Similarly, in the message passing example, the left thread issues 2 stores to X and Y, and the right thread reads from Y and then reads from X. And again, we want to know whether it's possible for the right thread to read value 1 for Y, i.e. observe the second store by the left thread, but read the initial value 0 for X, i.e. ignore the first store by the left thread. And just also to say that in these examples, for now, we can assume that the stores are plain stores. I've got nothing to do with non-temporal stores. So let's start with something simple. Well, we know that the very strong sequential consistency model, SC, doesn't allow any instruction reordering and doesn't allow either of these annotated behaviors, because these are known as weak behaviors and they're not allowed under Intel-x86 Semantics or SC. And as I said a few minutes ago, under the TSO model, we know that store and read reordering is allowed. So you can conceptually think of these two read operations being reordered before the earlier stores. And as a result, it will be possible to read 0 for both of these locations, but we won't be able to observe the message passing behavior. Now, remember, we want to know if this is the case for all memory types, so, and whether or not they follow the same model. It turns out that it's only the cacheable memory types, i.e. the WB and the WT memory types, that are subject to this TSO consistency and allow this right read reordering. And it's not necessarily the case for the other models. And just to give you a bit of a context, if you look at the Intel manual, it says that WB and WT both follow this ordering called speculative processor ordering, which is Intel jargon for TSO as we know it. But there is a caveat here in that the TSO only applies when all accesses or all locations in your program are in WB memory or they're all in WT memory. And the manual doesn't say anything about how different memory types interact with each other. So if you have a program where you have WB and WT together or WB and other types, how the behavior of that program will be. And also another bit of context, just to say that the text of the manual is really minimal, fairly laconic. It says very little about these ordering constraints and how you should understand them. And it doesn't say anything about how these accesses interact with each other. Okay, so we talked about non-cacheable cacheable types, WB and WT, and how they're subject to TSO. But what about the other memory types? Specifically, let's start with the easy one, the strong uncacheable one, UC. Well, as the name suggests, and you might have already guessed, it's a strong memory type in that it doesn't allow any reordering. And in that regard, it's precisely exactly like the SC consistency model. So neither of these annotated behaviors are allowed because you don't have any instruction reordering on the UC. And again, if you consult the manual, it refers to this ordering as strong ordering, which is Intel jargon for SC. And again, with the caveat that it only applies when all accesses in your program are on UC memory, and it doesn't say anything about mixed accesses. And here is again, just to convince you that the manual is not very helpful when it comes to understanding the consistency semantics of these memory types, because it says only 4 lines about UC, and 2 of them are about why and when you should use UC memory type. Okay, so we've looked at WB, WT, UC, and the only thing that we have to look at now is the WC memory, the non-cacheable write combining memory. Interestingly, from the point of view of these 2 examples, for WC memory, we see a mirror situation to TSO. So it doesn't allow store buffering, but it allows message passing. And this is because with WC memory, it doesn't allow write-read or store-read reordering, but it allows write-write reordering on different locations. So as a result, you don't observe the store buffering because you don't have write-read reordering, but because the stores in the left thread here can be reordered because on different locations, you can see the message passing behavior. And here is the description in the manual. It refers to it as weak ordering, again, which we have come to understand. It means write-write reordering on different locations. And here is, and with the caveat, of course, that only applies if all accesses are in WC memory. And here is the extent of what and how WC is described in the manual. So we have now an intuitive understanding of these different memory types and their ordering constraints. But what about the other thing that I mentioned at the beginning? What about non-temporal stores? Well, if you are to trust the text of the Intel-x86 manual, it says that non-temporal stores treat the memory being accessed as WC memory. And that is to say, using WC memory, the store will be following a weakly ordered, that thing that I just showed you semantics. In other words, the manual is telling us that non-temporal stores have the same semantics as WC memory. Of course, we trusted manual, but we also wanted to confirm and see whether this is indeed the case or not in practice. So when we actually went back and looked at these two litmus tests, it turns out that if we were to replace these two the stores in these programs with non-temporal stores, we actually can observe both store buffering and message passing. In other words, the WC memory type and non-temporal stores have different semantics, unlike what the manual suggests. So in that regard, the manual text is completely incorrect, and we have actually pointed this out to them. And this was why it was absolutely crucial for us to validate the Ex86 model that we have built to make sure that it's indeed what's happening in the hardware. Specifically, we have validated Ex86 using the DIY tool suite by Raad and others. And we've extended the K-litmus tool to allow us to specify different memory types by writing kernel modules. We have built a test space of over 2,200 tests. We have run each test on different X86 implementations, including Core i5, Core i6, and Xeon. And of course, we have run each test a large number of times, at least 600 million times, with some other critical tests run up to a few billion times. If you're interested to know more about our validation, it's available as a public artifact online at this URL on the screen. And also to say that in our paper, we have lots of examples of different weak behaviors, not just store buffering and message passing. And each time we have observed a weak behavior for a particular memory type or a particular scenario, we have accompanied it with a hyperlink to our test base, to our validation page. And you can go and have a look at how that has happened, the corresponding graph, and so on. Okay, so having done this extensive validation, we have built this comprehensive table of the possible ordering constraints for each of these memory types and which order is preserved or not. So here in the rows, I have the earlier in program order instructions, so reads and writes of different memory types, for instance, WB, WT, and NT stands for non-temporal stores, of course. And in the columns, I have also the later instruction in program order. And this table is indicating whether or not the ordering is preserved. So tick means order is preserved, as a result, no reordering is allowed. And cross means order is not preserved, so reordering is allowed. For instance, let's start with something familiar. We already know that WB memory is subject to TSO. We discussed this, and as a result, it allows write-read reordering, so the order is not preserved. Similarly for WT memory. By contrast, for UC memory and WC memory, we said that write-read reordering is not allowed, and the order is therefore preserved. For write-write reordering, we already know that TSO and WB memory don't allow write-write reordering, so the order is preserved, whereas for WC memory, we said that it allows write-write reordering as long as they're on different locations. So the order is preserved so long as the two writes are on the same location, denoted by this S log. And of course, there are some other simpler observations. For instance, unsurprisingly, the atomic update or RMW instructions and memory fences are very strongly ordered with respect to everything. So you can see you have ticks along both rows and with the corresponding row and the column. Okay, so our Ex86 model, without getting too technical, we have developed two different formalisms of Ex86, both operationally and declaratively. Our operational model is basically the same style as the original TSO model with different store buffers and the memory at the bottom. And our declarative model is, of course, in the style of different execution graphs. And we have, of course, proved these two equivalent because otherwise the two models wouldn't be that useful independently. Okay, so in the title, I also mentioned the persistency semantics. I talked about Intel-x86 consistency and persistency semantics. And so far, I've only talked about the consistency semantics. So what about persistency? What do we actually mean by persistency? So let's have a quick overview of that. So as you probably know, when we think about computer storage, you typically think in two separate ways, right? On the one hand, we have the RAM, the random access memory, which is faster access, but it's volatile, meaning that once power removed, when you have a power failure, it's lost, its contents are lost. On the other hand, we have hard disks, which are slower to access, but are persistent. And as you may know, there is this new and exciting class of memory technology called non-volatile memory, or NVM, which combines the best of both worlds. It's persistent and it is fast. Now, why would I be interested in NVM in a talk about semantics? Well, it turns out that in the context of NVM, when you run your programs on top of NVM, there are some interesting behaviors, even in the case of sequential programs, even if you completely ignored concurrency. So let me give you a quick example of that. So here I have a sequential program with two locations, X and Y. Let's assume again, for simplicity, that these are the default WB memory, and these stores are plain stores. So I write one to X, I write one to Y, and then I have a power failure, right? And so I'm going to restart my machine, and the question is, what possible values should I be observing for X and Y? Well, one might argue that, okay, you said this is in the context of NVM, so it should be non-volatile, and I should recover all of my work afterwards, so X and Y should both be 1. And that's definitely one of the possibilities. But it turns out that for performance, execution can go ahead of persistence, meaning when you issue a store, it doesn't necessarily get persisted to memory immediately. In fact, we know this. It may sit in the cache hierarchy, right? And if you don't have persistent caches, and your program crashes before either of these writes have persisted to memory, then of course, when you restart the machine, you will have lost all of this work, and you will see the initial value 0 for both of them. And similarly, if this first write had persisted to memory and the second write hadn't, then you would see the first X is 1 and Y is 0. But most surprisingly, it's also possible for you to observe the second write, but not the first one. And this is because, again, for performance, the writes don't necessarily persist to NVM in the same order they were executed, or even in the same order they were made visible to other threads. So if they were reordered, if they persisted out of order and you had a crash between the two, then of course you will see Y is 1 and X is 0. And this is what I meant by, even in the case of sequential programs, there are some unexpected behaviors. And this is why it's important to understand the persistency semantics of programs. Okay, so just a bit of terminology. When we talked about consistency model, as you already know, we really meant the order in which writes are made visible to other threads. Whereas when we talk about persistency, we really mean the order in which writes are persisted to NVM. So to have full semantics, we really have to talk about consistency and persistency together. And this is what we have done here. We have built another model, an extended model called PE-X86 for persistent extended X86 that talks about consistency and persistency semantics of X86 architectures, including these additional features of non-temporal stores and memory types. Of course, unsurprisingly, we have done this in two different ways, both operationally and declaratively. Our operational model is an extension of the original TSO model, where we add an extra layer, this persistency buffer, in order to capture the out-of-order persistence of different writes, as you saw in the previous example. And once again, we have proved these two different models equivalent. Now, I'm not going to show you any more examples of persistency, but just to quickly tell you that if you're interested in our paper, we have lots of examples. Here is some of them with regards to the persistency semantics of different memory types, when combining plain stores and non-temporal stores, such as this one here, and their interaction as well, when one write is on WB and the other is on WC, and so on, and all the possible combinations. So if you're interested, please go have a look at that. And with that, I come to the end of my talk. Just wanted to say a few concluding remarks, give you a summary of what we have done. We have developed the Ex86 model, the extensive consistency semantics of X86 that includes memory types and non-temporal stores. We have formalized these both operationally and declaratively and proved them equivalent. We have validated our consistency model extensively, as I showed you. And we have also developed the PE-X86 model for consistency and persistency of X86 architectures, including these additional features. And we've done so both operationally and declaratively, showing that they are equivalent. Of course, there's a lot more to be done in the future in terms of verification for these models, program logics, model checking algorithms, and so on. But for now, that's all I have to say. Thank you very much for listening. Okay. So Yes, I can. Yes. Okay, so should I? Okay, I'll read that for myself. I imagine everyone else can do the same. Um, pairwise thread local reorderings. Okay. Um, well, essentially, I think what Peter is asking is we've always been suspicious that the WC memory or non-temporal stores would expose non-multi-copy atomic behaviors. In fact, as you probably already suspect, Peter, our tests include the IRIW example as well, and so far we haven't seen that weak behavior at all. So, uh, as far as one can trust the validation effort, which like I said, we have run the tests repeatedly on many different architecture and many different implementations. We didn't observe any non-multi-copy atomic behavior. So for now, we're assuming that they do not cause any non-MCA behavior. I think so. Okay, I'll have a look at it before. So like I said, Peter, I don't know, hopefully that answered. We haven't seen any non-MCA behavior. As far as comments from Intel are concerned, I have emailed Gil. You probably already know him, Gil Niger. I told him that this is our model and this is what we expected. He said he's not at all surprised that there's there is disagreement when it comes to the semantics of WC and non-temporal stores and how they should really be implemented. But he said that it is actually good to know that there is a difference between them and that they should clarify the behavior in the manual. The comments were positive as far as I can tell, but also to some extent, engineers can be a little bit more laid back about this sort of thing. They were not that surprised, but they did note that there is a discrepancy in the manual.